Let's take a look at how we worked out the practice problems that we created for Unit 2 in the new CED. So if we look at the first one, RB20, our choices are either molecular, ionic, or a network solid with covalent bonding. A network solid with covalent bonding is kind of one of those special cases that will show up in a later unit. Typically, we think of it as being quartz or diamond, those kinds of things, silicon dioxide. A molecular solid with zero dipole moment versus a molecular solid with dipole moment, those are basically saying covalent and either nonpolar or polar. And then finally, ionic. So the first one's easy. Solid RB20, rubidium oxide is a metal and a nonmetal, so it's got to be an ionic solid. For carbon dioxide, we know that that's two nonmetals, so that's a molecular solid. But is CO2 a polar molecule or a nonpolar molecule? So we draw out a basic Lewis structure, and you'll notice that the CO bond is actually polar. Oxygen is more electronegative. But the oxygens are directly opposite each other, and so the pull on the electrons are being pulled towards the oxygen, offsets each other. So CO2, even though it has polar bonds, is a non-polar molecule. So the correct choice there would be B, a molecular solid with zero dipole moment. All right, number 3 has to do with the lattice energy calculation. Lattice energy calculation is very similar to Coulomb's law, where Q1 and Q2 are the charges and R is the radius. So it will either be about the radius and the charges will be same, or the radius is unimportant and we only worry about the charges. So the charges of magnesium and oxygen are +2 and -2, whereas for sodium and fluorine is +1 and -1. So which answer sounds like that the charges matter? And when you come down and look over all the answer choices, B is the only one that makes any kind of sense. A is not true. C is not true. That would have to do with radius, and we know in fact that the fluorine ion is actually smaller, and it has a more complex structural lattice. That's just putting out a bunch of words, hoping someone will pick it. For question number 4, they're telling you that the experimental bond length is 140 picometers. A single bond is 134, while a double is 154. So we know it's somewhere in between. Which one of the following reasons is a correct explanation for why it doesn't match? Why isn't it 134 or 154? Why is it somewhere in the middle? The presence of both double and triple bonds, that can't be it, because if you notice, there are double bonds but no triple bonds. The carbon atoms have both sp3 and sp2 hybridization. Well, all the carbon atoms actually have sp2 hybridization. But even if it was sp3 hybridization, that doesn't necessarily have to do with bond length. That has to do with how many regions of electrons are there. So the only answer that makes sense here is it's not really a single bond and it's not really a double bond, that it is somewhere in between. So the correct answer here is D. It's not a single bond, it's not a double one. It would actually have a bond length somewhere in between the two because of resonance. This is more of an old school type question that's pretty simple and not a whole lot of reading. So which diatomic species has the largest bond dissociation energy, meaning the energy it would take to break that bond and free them apart? So if we look at the 4 structures, you'll notice that the highest bond energy is going to have to be the triple bond, but there would be 2 triple bonds. Now I will say B2 is not a normal Lewis structure, so you can usually get rid of that kind of thing. But even between the two, the nitrogens are going to have a stronger pull on each other because there's just simply more protons there. So there's more attraction to the electrons. So which one has the largest bond dissociation energy? That would be C, nitrogen. Which diatomic species has a bond order of 2? Well, bond order is just simply put, what is the number of bonds? So fluorine has a bond order of 1, oxygen has a bond order of 2, nitrogen 3, and boron 3. So the answer there would be oxygen, and that would be D. Which diatomic species contains 1 sigma and 2 pi bonds? So 1 sigma and 2 pi means that there's a single bond. That would be the sigma bond, the first one that forms, and then 2 pi bonds means it has a total of 3 bonds in between them, and the correct answer there would be C, because in all honesty, this Lewis structure right here is one you really can't draw because you can't get to 8, and it's not one of the common diatomic species. Which of the following has the shortest bond length? Again, a single bond is going to be longer, a double bond is going to be less long, and a triple bond is going to be the shortest. So based on what we saw before, this one right here, the triple bond will be the shortest bond length and also the highest bond energy. For number 9, it's ionic, but it has sigma and pi covalent bonds. Ionic because it's got a metal, but how can you have both ionic things and covalent things? What you have to remember is that any polyatomic ion, like hydroxide here, is a covalent ion. So it's a molecule that's covalently bonded inside the molecule, but has an overall charge. So the hydroxide in iron hydroxide would be just a single bond. So that would only be a sigma bond. So that one's out. H2S, that would not be ionic at all because that's a covalent molecule. NaCN would be the cyanide, and if you had to draw out the Lewis structure for cyanide, you'll see that it's got both a sigma bond, the first bond that forms in between them, and 2 pi bonds to make up that triple bond. So the correct answer there is D. Which one of the following would have 2 unshared pairs of electrons on the central atom? So to do this, you would have to draw it out. And I drew it badly above, so let me try again. Here's sulfur dihydride, or hydrogen sulfide. And you'll notice that sulfur, when you draw the complete Lewis structures, has 2 lone pairs around it and 2 bonding pairs. This is supposed to be a single bond to this hydrogen. So that's going to have 2 unshared pairs of electrons. NH3 classically has 1, CH4 has none, and HCN on the central atom, and we drew that before up here, HCN on the central atom would have no lone pairs. So the correct answer there is H2S. So you would have to draw out the Lewis structures for these. So BCl3, boron is one of those atoms that's happy with 6 electrons. So boron is going to have 3 chlorines attached to it. CHCl3 is going to have the hydrogen and then the 3 Cls. So that can't be planar, that's going to be tetrahedral. And the NCl3 is going to have a nitrogen, 3 Cls attached to it, and then you still have a lone pair. So you'd have to draw out the 3 of them to get an idea of what the Lewis structure is, but there's only one that's planar, and that would be the BCl3. Same thing for 12. You're going to have to actually draw out the Lewis structure. The chlorine is going to have 3 lone pairs around each chlorine atom. The nitrogen is going to be a triple bond with a lone pair on one side and a lone pair on the other. So that would be 2 unshared pairs. NH3, and again, we've seen that one before classically. It's very similar to this one right here, and that would be 1 lone pair. So the correct answer there is going to be C, NH3. For number 13, again, you're going to have to draw them all out, and when you draw them all out, you'll get a shape for each one. So for CCl4, that's going to be tetrahedral. For CO2, that's going to be linear. For PCl3, what I want you to notice is PCl3 is going to look very similar to this one up here at the top, the NCl3. So that's going to have a trigonal pyramidal look to it. PCl5 is going to be phosphorus in the center, surrounded by 5 different things. And that's going to be trigonal bipyramidal. So a pyramid on top and a pyramid on the bottom. And SF6 is going to be octahedral. So you basically have to assign a shape for each one, go through, and then try to figure out what's going on. And the only one we don't see all over the place is this idea of square planar. Pi bonding only occurs in double or triple bonds. So we know that there's a double bond here. We know that there's a triple bond here in cyanide. We did that one earlier. We know in CH4, those are all single bonds. So since those are all single bonds, we know that the answer is CH4. And in C2H4, if you drew that one out, you would have two carbons connected with a double bond, two hydrogens on one side, two hydrogens on the other. So a molecule that has sp3 hybridized orbitals, what does that mean? It means there are 4 orbitals. Each one of those orbitals is an sp3 hybridized orbitals, each one. So if you have 4 orbitals and they have to get as far away from each other as possible, then 4 things would be tetrahedral. So you can describe the electron geometry by just thinking about how many places are there where you find electrons. There'd be 4 sp3 hybridized orbitals, and so the shape would be tetrahedral. Which of the following has a dipole moment of 0, meaning it's non-polar? Classically, any hydrocarbon is non-polar. NO is a very simple, oxygen pulls more on the electrons than the nitrogen, so NO can't be it. NH3 is classically a polar molecule because it's trigonal pyramidal with the lone pair on top, and the electrons actually get drawn up to the nitrogen, showing that the nitrogen side of the molecule is negative and the hydrogen side of the molecule is positive. For SO2, you would have sulfur in the middle with a lone pair above it. You'd have a double bond to one oxygen and a single bond to the other. This is actually going to make this a bent molecule. If it wasn't bent, then you could say, oh, this is a non-polar molecule. But because the shape of this is sulfur up here, the oxygen's coming off at an angle, we're going to create an area where the electrons spend more time at the bottom making a negative charge and less time at the top making a positive charge. The biggest dipole moment is the greatest difference in electronegativity. CO2, we've already said, is non-polar. That can't be it. O2 is an oxygen attracted to an oxygen, very non-polar. Carbon monoxide would be polar a little bit, but H and F have a huge difference in electronegativity between the fluorine and the hydrogen, and that huge difference in electronegativity means it's going to be the most polar. It is so polar that HF molecules form hydrogen bonds. Which of the following has a 0 dipole moment? Again, you would have to draw out the structure for each one and figure out whether it is polar or nonpolar based on shape and distribution of electrons. Everything else except for C is polar because of the way that the elements are arranged around that central atom. Draw each one out and see, but for PF5, there's phosphorus in the center with fluorines evenly distributed around it, and there is no unequal distribution of electrons. It's very much the same throughout the whole molecule. Resonance are necessary when you have a double bond and a triple bond, or a single bond and a double bond, or something like that. So if all you have is single bonds, you don't need resonance structures. If all you have is double bonds, you don't need resonance structures. So again, drawing this out, H2S, that looks like water. That's going to be all single bonds. CO2 is only going to be double bonds, and OF2 is going to be only single bonds. Draw it out. So the only one that's different is SO2, and we did SO2 previously because sulfur has a single bond on one side and a double bond on the other and a lone pair. So because of the double bond and single bond, it would take drawing a resonance structure saying, hey, that double bond can live on the left and not on the right. So both are okay. For number 20, we want to start in order of decreasing. So we want the one that is the most polar first and goes to the least polar. So B is a good choice if you didn't read directions. That's actually going from least polar to most polar. A here is the answer because you're going from a very, very polar bond HF down to an FF bond, which has a dipole moment of 0. For number 21, it would actually have you calculate the electronegativity difference, and the greater the electronegativity difference, the greater the bond polarity. So you would have to actually go in here and calculate for CH4, the carbon is 2.5, the hydrogen is 2.1. That's an electronegativity difference of 0.4. And so you'd write that down, and then you would do the same thing for SiCl4 and SF4. Notice that it doesn't give you different molecules for every single answer choice, but you would have to do the electronegativity difference for each bond, S and F, C and H, Si and Cl, and then rank them from least polar to most polar. So the correct answer there is A. And number 22, which one is going to have the greatest solubility? That's another way of saying which one is the most polar. Water is a polar solvent, so it will want to dissolve polar things. And CH4 is nonpolar, CCl4 is nonpolar, NH3 we've already established is polar because it's trigonal pyramidal, and so that would be the answer. Number 23 and 24 have to do with this graph. This graph shows the internuclear distance between two nuclei in some unknown diatomic molecule. So what would the bond length be? Well, your choices are 2, so up here, 3 up here, 0.9 up in here, and 1.1 down in here. So where is a bond actually formed? A bond is formed at the place of lowest potential energy, so down here, so at the bottom of the curve. And what is the value of the x-axis where it reaches its minimum? That would be 1.1. For number 24, at that bottommost part, that's the point where the attractive forces are equal to the repulsive forces. So here, there's more attraction than repulsion. The nuclei are farther away. Up here, there's a strong repulsive force because the two nuclei are getting really close together. And so you don't want things too far away. You don't want things too close. You want them to be just right. So you would have to draw out PCl5, and we've actually seen this before. Basically what I'm trying to show here is there's a pyramid on top and a pyramid on the bottom, so that would be trigonal bipyramidal. So PCl3 for number 26 looks something like that. You have a lone pair on top. Now normally, if it had been PCl4 or something like that, you would say, oh, this is a tetrahedral shape, and tetrahedral is 109.5. But when you have a lone pair on there, it pushes more on those bonds than a bonding pair would. So that means that bond angle actually gets squeezed a little bit more. So the bond angle should not be 109.5, it should be slightly less than 109.5. So now you have to pick between C and D because they both have less than 109.5. In letter C, the reason why it's wrong is the chlorine atoms have lone pairs around them, but you only consider the lone pairs around the central atom when you're thinking about shapes and bond angles. So the correct answer there is D. The lone pair on the phosphorus is pushing harder on those bonding pairs than the bonding pairs would be pushing if it was tetrahedral. Classic alloy questions. You've got big circles and you've got little circles. When you have big circles that don't seem to be interrupted and you've got little circles that are strewn throughout kind of in the spaces between them, that's always interstitial. Substitutional would be one of these great big circles was taken out and replaced with some other kind of metal. Distributed isn't even a thing, and a metalloid alloy isn't really one of the types of alloys that we need to worry about. When you have a substitutional alloy, they have to be similar in size. So that's the correct answer here, C, and that's just a definition thing. Lattice energy, again, comes down to the lattice energy equation, which is always going to be a type of Coulomb's law. So again, it's either about the charges or it's about the radius. Let's see what this one is. KF has a charge of +1, -1. LIF has a charge of +1, -1. So this isn't a Q question, this is an R question. So the smaller the R, the smaller the radius, the greater the lattice energy. And that's because of the attraction for the nuclei with those electrons. So the smaller the radius, the greater the lattice energy. So since Li has got a smaller radius, then the only answer that matches up with that reasoning is letter D. Kf has a larger internuclear distance, and when you plug a big R in there, that means it has a smaller lattice energy than LiF does. If you have to test whether something is ionic, metallic, or molecular, you're going to look at a whole host of things. Does it dissolve? Does it conduct electricity? Is it malleable? Those kinds of things. So, two electrical leads are connected to the solid, but no electricity is found. So we have to automatically take out the metal, because we know that metals do conduct electricity in their solid state. When the leads are put in a solution of it, so meaning it's been dissolved in water, electricity is conducted. So we want something that's an electrolyte. We want something that when you add it to water dissolves into ions. The only one of those that's possible there is KCl. So KCl is the answer. This thing right here, your students may say, oh, hydroxide's a polyatomic ion. Well, but this is a molecular compound, and so CH3OH is methyl alcohol, and even though it will dissolve in water, it doesn't split into ions. SiO2 is a classic network covalent compound, and that's all covalent bonds all the time. And that will be covered more in depth in a unit later on.